Hello and welcome to Weapons of Math Instruction. Thanks for tuning in to day 2 of our E-Day celebration. If you missed the first video, you can find it on any of my social media accounts, which are listed at the end of this video. So in the first video, I gave an informal overview of the various definitions of E, as well as of exponential growth and decay. In this video and the next video, I'll take a closer look at the definitions that I presented in video 1. So in the first segment, we'll examine E as the limit of a sequence. And just to refresh your memory, here is that first definition. As n gets closer to infinity, this expression 1 plus 1 over n to the power of n gets closer to e. And in the limit at infinity, the expression is exactly equal to e. Now, infinity is not some number that we could just plug into the expression. So to get our heads around this, we'll cap off the value of little n at some point, which I'll call capital N, to get approximate values of e. And we'll denote the nth approximation of e as e sub n. So here I plugged in 1. So if I plug 1 into this expression, I get 1 plus 1 over 1 to the first power, and that's just 2. So we had the first digit of e. Remember, e is about 2.71828, etc. Okay, if I plug 2 into this expression, I get 1 plus 1 over 2 to the second power. That's 2.25. We're getting closer to e, but we're getting there extremely slowly. Let's speed things up a little bit here by picking a bigger number. So here I've chosen 10, which is 1 plus 1 over 10 to the 10th power. And still, we don't even have the second digit yet. So it's 2.59374. The 10th digit of e is 7, remember. So this job is better left to a computer. And so now we will turn to the computer. So here, I've written a C++ program to do this work for us. So the program asks for the value of capital N, and then it calculates the nth approximation of E, and it spits it out. So let's run this program a couple, 2-3 times. Okay, so we left off on the slide at n equals 10, right? So I'm going to jump up to a bigger number, let's say 100. Okay, so E sub 100 is 2.70481. We've got the 10th digit of E finally. All right, let's jump it up even higher. Run it again, say 1,000 this time. And now we have the 10th and the 100th digit of E nailed down. I'll just do it one more time. 10,000. Okay, now we got 2.718, so we're correct to the thousandths place. And you see, as we increase the value of capital N, we get closer and closer to the value of E. Okay, we're back. So now let's get into segment 2, where we'll look at E as an infinite series. And here's definition 2. E is the sum as n runs from 0 to infinity of 1 over n factorial. And here I've listed out the first 4 terms. Now, we can't sum infinitely many terms, but what we can do is cap off the value of little n at some value capital N to generate approximations of E, just like we did when we looked at definition 1. So let's do it. So E sub 1, this is where we stop the series at n equals 1. So we include the n equals 0 term and the n equals 1 term. And something I should point out is 0 factorial is defined to be 1. So this is 1, and 1 factorial is 1, so we get 1 plus 1 is 2. So there's our first approximation for E. E sub 2 includes the first 3 terms for n equals 0, 1, and 2. And this is 1, this is 1, 2 factorial is 2, so this is a half, so we get 2.5. And we'll do it one more time. So here's E sub 3. And if we generate those terms going up to n equals 3 and add them up, we get 2.6 repeating. So we're getting there fairly slowly. So just like we did with definition 1, let's turn to the computer again. Okay, so here I've written a C++ program to calculate definition 2. And C++ does not have a native factorial function in the standard library, so I went ahead and wrote one up at the top here. And the main function that calculates definition 2 will call this function. So the program asks for the number capital N, which is where we cap off the infinite series. And down here it calculates it, term by term. And down here it spits out the approximation. So let's run this program a few times. So on the slide we left off with E sub 3. Let's try a bigger number, say 5. So E sub 5 is 2.71667. That is correct to the hundredths place. do it again with a bigger number. 7. Okay, E sub 7, 2.71825. This is correct at the thousandths place. Let's kick it up one more notch here. Well, a few notches. I'll say 10. And E sub 10, 2.71828. All these digits are correct. So there's no point in continuing because my computer can't do any better than that. And we're back. Moving right along, let's look at the third definition, in which we consider E as the base of the natural logarithm. Now, there are a few facts about logarithms that I need to unpack here, so I'll try to be as complete as possible while also being as brief as possible. So, first, a logarithm is essentially an exponent, and I'll explain what I mean by that shortly. Next, logarithmic functions have a base, which I'll call b, and acceptable bases for logarithms are positive numbers, but not 1. And here, we're not going to worry about why these restrictions exist on b. We'll just note that e is a positive number, and it is not 1, and so it's an acceptable base for a logarithm. The notation for a logarithmic function is log base b of x, where the b is written as a subscript. So let's take a look at a first example. We'll keep it simple at first. We'll look at log base 2. So we're going to take log base 2 and plug the number 2 into it. Now 2 is the same thing as 2 to the first power, or 2 to the exponent of 1. And remember up here when I said that a logarithm is essentially an exponent? If the base of the logarithm matches the base of the exponential expression inside the logarithm, then the result is the exponent. So this 1 here in the exponent is that 1 there. Let's bring that idea home with another example. Log base 2 of 8. 8 is 2 to the power of 3, so the exponent is 3. And see, the base of the log matches the base of the exponential expression inside the log, so the result is the exponent. So that's what I mean by a logarithm is an exponent. That's how it was taught to me in 9th grade algebra, and I never forgot it. Okay, now we're not here to talk about log base 2. We're here to talk about log base e. So, the logarithm in base e has a special name. It's called the natural logarithm. For reasons we won't get into in this video, e is considered the natural base. And we denote it as either log base e of x, or more commonly as ln of x. And that's the notation I'll be using in the rest of our discussion. Now, if you take Calculus 1, you learn that the natural log of x is defined in terms of this integral here. It's the integral from 1 to x of the function 1 over t dt. And this is only defined for x greater than 0, positive x. So this implies that the natural log of e, which is the integral from 1 to e of 1 over t dt, is 1. Why? Because this is the log in base e, and e can be thought of as e to the first power, so the result has to be the exponent on the e, which is 1. Now, if you haven't taken Calculus 1, all you really need to know about this operation that I've called integration, which is denoted by this squiggly line here, is that integrals are related to areas. Let me sharpen that point a little bit. So since this function, f of t equals 1 over t, since it's greater than 0 for all t's in the interval of integration from 1 to x, the integral from 1 to x of 1 over t dt is the area between the graph of f of t and the t-axis. Okay, that's a lot to take in if you're a math noob. So a picture's worth 1,000 words. Let's go to a picture. Okay, so here I've got a picture that I've generated with a free program called Geogebra, and I love this program. As a matter of fact, I'll put a link in the description on the YouTube video. So I've labeled the vertical axis y, I've labeled the horizontal axis t, and on the t-axis, I've also labeled the point where e sits. So it's sitting right here. This is 2.6, this is 2.8. E is sitting right about there at 2.71828. And here's that operation of integration. I'm going to issue the command integral f of x, and then I set the limits on the t-axis from 1 to e. And what that's going to give me is, as described on the previous slide, the area of this shaded region, which is the area between the graph of f of t and the t-axis, between the limits t equals 1 and t equals e. And you can see it. It's kind of small at the bottom here. It says A equals 1. That's the value that it calculated. It's also here in the algebra menu. Geogebra calculated the area to be 1. And that's exactly what it should be, because the value of this area is the natural log of E, which has to be 1. So hopefully this adequately illustrates what I was talking about on the last slide. All right, one segment to go. In this brief segment, I'm going to give you a sneak preview of the next video. An important question to ask is, how do we know that the 3 definitions of E that we discussed in this video all define the same number? For instance, with the sequence definition and the infinite series definition, you can generate digits of E all day long, but E has infinitely many digits, so you can never know that all the digits match just by generating approximations of E. So what we need to do is we need to show that the 3 definitions are equivalent, and that has to be done with a deductive proof. So here are the 3 definitions that we looked at. Here's E as the limit of a sequence, here's E as an infinite series, and here's E as the base of the natural logarithm. What we need to do is prove that each definition implies the other, and that will be a proof of equivalence. So this will give me the opportunity to show you a nice bit of mathematical reasoning. Well, thanks for tuning in, and I'll talk to you soon in the next video. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.